Hi, let's see how to make spectrograms in Python with the help of the short-time Fourier transform. We'll use Librosa and its corresponding function stft to compute a short-time Fourier transform. In a new cell, type S, which is a standard naming convention for a variable storing a spectrogram obtained with stft. Then, after the equal sign, type librosa.stft. In parentheses, put the variable containing the audio data of our file. Remember, this variable contains the time amplitude representation of the sound. Therefore, this is the representation we'll transform into the frequency domain. Let's execute. The function breaks the audio signal into short overlapping segments and applies the Fourier transform to each segment, resulting in a complex valued matrix stored in the variable S. Each value in S tells us how strong a particular frequency is at a specific time. But looking at these raw numbers can be confusing. We need to convert the amplitude values in S to decibels to make it easier to understand. They are part of a scale that represents how humans perceive sound by giving us a clearer picture of the loudness of each frequency. Okay, let's do that using Librosa once again. Create a new variable and call it SDB, deriving from decibels. Then type librosa.amplitude to decibels, a function that will do the conversion for us. It seems that Librosa took care of everything. We must pass two arguments here, so let's break down what's happening. First, the short-time Fourier transform calculates the frequency components of the audio signal and stores them in S. The values in S are complex numbers which have two parts: the amplitude, which is the magnitude or length of the complex number, and the phase, which tells us the timing or position of the wave. But since we're only interested in the amplitude, we use abs-s to extract it. The abs function calculates the absolute value of each complex number, which gives us the amplitude for each frequency in the audio. Now, the amplitudes can vary greatly and aren't directly related to how we hear loudness. For example, an amplitude of 1000 doesn't sound 10 times louder than an amplitude of 100. So we need to convert these values into decibels, which are easier to understand. The Librosa amplitude to dB function converts this for us, making the values more useful for analysis. Ref equals to np.max ensures the highest reference value is 0 decibels. Let's check that out by calling the function separately. See? Setting the reference level to the maximum value in the amplitude spectrum normalizes our values. This means the loudest point in our spectrum will be 0 decibels, making it easier to understand and compare. It simplifies understanding the dynamic range by showing how quieter other parts are relative to the loudest part. This normalization aligns with standard audio analysis practices, making the data more intuitive and consistent for interpretation. Okay, good. What's left is to visualize the spectrogram. I'll create a new plot figure with a specific size of 12 inches by 4 inches. Then I'll use librosa.display.specShow to display the spectrogram. In the parentheses, I'll use data equals SDB to show the decibel scaled spectrogram. And SR equals sample rate is used to define the sample rate of the audio signal and label the time axis. To set the x-axis to represent time, use x-axis equals time. The x-axis parameter expects a string value, and one valid option is time, which configures the x-axis to display what we need. Y-axis equals log is used to set the y-axis to a logarithmic scale, commonly used for visualizing frequency data. plt.colorbar will add a color bar to the plot to indicate the spectrogram's decibel levels. The following value of the format parameter will display the color bar labels with no decimal places. We're almost done. Let's define the graph's title and XY labels as spectrogram, time, and frequency. Finally, we'll use plt.show to display the spectrogram. All right, I think we're ready to execute. Excellent. Now we can analyze what we see here. On the left y-axis, we have the frequency range from 0 to about 16,400 Hz, covering all audible frequencies, with lower frequencies at the bottom and higher frequencies at the top. The right y-axis displays amplitude in decibels ranging from -80 decibels to 0 decibels. Here, 0 decibels marks the peak amplitude, while -80 decibels indicates much quieter sounds. The more yellow the colors, the louder the sounds. Human speech typically falls between 80 and 250 Hz for fundamental frequencies, with harmonics extending to 8,000 Hz or higher. Notice the yellowish tones between 64 and 256 Hz? Their color indicates that they are the loudest in the recording. Additionally, they coincide nicely with the fundamental frequency of human speech. We can conclude that this is primarily where speech occurs in the recording. We hear the background noise in the file during quieter intervals where no speech is recorded. These regions show various frequencies, though not very loud. Furthermore, the audio's last 1 or 2 seconds contain almost no noise. Focusing on this part of the spectrogram reveals the missing noisy frequencies compared to the rest of the graph. These are mainly in the range of 512 to 2048 Hz and higher. We can try removing some of these frequencies from the whole file and hear if it sounds better. Of course, we can't remove all sound of these frequencies because in this case, we would also be removing some of the speech. Actually, we don't need to do that manually, you know. Python has its own methods for dealing with noise. Stay tuned for the next lesson where we'll explore this topic further and work on filtering out some of the noise. See you then.